Alright, welcome to Experimental Design Part 2. Hopefully you already watched my first video, Experimental Design Part 1. If you haven't, I'd highly recommend stopping this video and going back and watching that one, because you need to learn the basics of experimental design before you can understand what I'm about to talk about in this video. Now, what I want to talk about this video is that there are three different designs for an experiment. There are three different ways that you can design your experiment and have it work. Okay? Now, a lot of the major pillars that we talked about in the previous video, we talked about control, we talked about comparison, we talked about randomization, we talked about replication, okay? All of those four major pillars are in every one of these three design types. But they're all a little bit different for important reasons. So I want to talk about three different design types. Now, in order to talk about the designs, I want to talk about an example with you. So here's the example. Will a new pill help relieve knee pain? Okay? So I got a new pill. And will it help relieve knee pain in people that have pain in their knees? So explanatory variable is my pill, and knee pain is my response variable. Okay, so the first design type is what's called a completely randomized design. In a completely randomized design, the subjects are assigned to the treatment groups completely by chance. Completely by chance. So what happens in a design like this is, let's say I have 100 subjects. Now these 100 people, they can certainly be volunteers, because I need people with knee pain, and I can't randomly pick people with knee pain. So it's completely okay if I have 100 volunteers who all come to me with knee pain. Now these 100 people are of different ages. They are different genders. They have different severity of their knee pain, and they also have different medical histories. Okay? And they also have different diets. They also have different exercises patterns in terms of how much they exercise. I mean, there's a lot of differences about these 100 people. But here's the idea in a completely randomized design. No matter what, everybody gets a number, 0, 0 through 99. The first 50 people chosen will get my new pill. And the remaining 50 people will get the placebo. Hopefully you watched the previous video to understand why they need to have a placebo. So once again, who gets what is completely up to chance. Now, I have comparison. I have replication. I got 50 people getting the new pill, 50 people getting the placebo. Be careful. I could have another group. I could have a third group that gets a current pill already on the market. That would be completely fine. I could also do new pill 50 milligram, new pill 100 milligram, new pill 200 milligrams, and then a placebo. There's a whole lot of different things I can do. I stuck with just two groups. Remember, you got to have at least two. And then what's going to happen is I'm going to wait 6 months after them taking that pill. They're all going to take the pill in the morning with a full glass of water, empty stomach, and they're going to take the second dosage at the night with a glass of water with an empty stomach. And they're going to do this for 6 months, taking the pill twice a day, every day, in the morning and in the night. So again, that's me establishing control so that other things don't become confounding variables. Okay? Like when they take the pill, did they take the pill with food or without food? As long as I control all that, I've handled any of those variables. And then after 6 months, I'm going to have a doctor analyze their knee pain, and I'm going to see whose knee pain has subsided the most. Now, somebody might always do one of this. Well, what if all the boys got put in the new pill group and all the girls got put in the placebo group? Now, obviously, that would be very bad. But come on. We're doing this by random chance, right? There's very little chance that that's going to happen. Both groups will probably get both boys and girls. Well, what if the severity of pain in the people that have the new pill, they have a lot more pain. The people that go to the placebo, they have very little pain. Once again, that would be extremely rare to occur. Chances are you're going to get both levels of severity even high, medium, low severity in both groups. Same thing with people that eat healthy. They're going to be in both groups. Same thing with people that exercise. They're going to be in both groups. It might not be exactly even, but you're going to get a good mix of people in both groups, ensuring that you have two very similar groups except for what pill they're taking. Now, if somebody really wants to play that what if game, one thing I can do is up the replication. If I have 1,000 people, 500 with the new pill, 500 with the placebo, now, like we've talked about in the past, replication helps because if more subjects are used, there's a better chance that those variables that you guys are talking about, age, severity, exercise, diet, all of those variables become diminished when I use more people. Hopefully that makes sense to you guys. I mean, think of it like this, right? If I only use 10 people, that's all I use is 10 people. 5 and 5. And these 5 show a small change. Or I use 1,000 people, and these 500, and then there's 500 here, and these 500 show a small change. What is more meaningful? 5 people showing a change or 500 showing a change? 500 is clearly more meaningful, which is why replication is important. Okay? So randomization helps balance all the variables we cannot possibly control for. So I listed 6 variables there that I cannot possibly control for. Randomization will help me balance them out between the groups. Add in replication, and all of a sudden, all those variables that some people play that what-if game with, those variables get diminished. That's completely randomized design. Who gets what treatment? Completely random from the get-go. Very easy to understand. The next design type is called randomized block design. Here, subjects are first placed into groups or blocks. That's where we get the name from. So they're first placed into blocks based on one variable that they have in common. That is of major concern to the response variable. Then, within each group or within each block, all treatments are handed out randomly. The idea is this: if you really think that one of those other variables, besides the explanatory, might truly have a response, or might truly have an effect on the response, then what you do is you could block for it. So let me explain this based on my example. So I'm going to come to the side here for 1 second. Let's go back to my 1,000 volunteers who have knee pain. If you are convinced that exercise plays a huge role in pain going away or pain staying, then you might want to block based on exercise, which means you're going to have your 100 subjects fill out a survey about how much they exercise. Then you're going to put them into groups. People that exercise a lot, people that exercise a medium amount, and people that exercise very little. You could even have a group that exercises not at all. Okay? How do you determine who goes into which group? Well, that's based on a survey. You cannot control that. Let's just say that you have 20 people that exercise a lot, 10 people that don't exercise at all, 50 people that exercise a little bit, and 20 people that exercise a medium amount. And again, you determine what level you want medium to be. Twice a day versus exercise a lot is 3 times a day. Whatever. That's completely up to you as the researcher. But what happens here is this is not random at all. This is by blocking. You are creating groups based on a similar variable. Then, in each group, you run basically a completely separate experiment. So of those that exercise, 10 will randomly get the new pill, and 10 will get the placebo. How will that be done? Randomly. That will be done with the capital randomly, right? Then, capital randomly, capital R, right? Okay, so then of those that exercise a medium amount, 10 get the new pill, 10 get the placebo. Exercise little, here it's going to be 25 and 25, new pill versus placebo. And down here, 5 get the new pill, 5 get the placebo. Now, if you're concerned that 5's not enough, add more subjects, increase your replication. So hopefully that makes sense. Then the idea, the value in this is I could see maybe my new pill only works for people that exercise a lot. So I find that out because I was able to block, and I find out that it's the combination of my pill and exercising a lot that will make your knee pain go down the best. Whereas if you take my pill and you don't exercise, you might lose a little bit of pain, but because you're not exercising, you still have the pain. So when you block like this, what it allows you to do is it allows you to reduce the variability. Right? Now you are looking specifically at people that exercise a lot, and you now have one less variable in that group to worry about. And then you could deal with, does your new pill actually work? And then in this group, again, they're all very similar. It's one less variable to worry about. You've reduced the variation within that group, and now you could really decipher, does your new pill work better than the placebo for those people and how much they exercise? So a couple of key things is you can only block on one variable. So choose what you think is the most important if you want to block. Again, there was the option of a completely randomized design. This is just another option if there is a variable that is standing out that you need to block on, okay? Let me just run through one more example, just extremely quickly here. Let's just say that you think age is most important. Okay, then you're going to block by older people. Maybe old is defined by anything over 60. Middle-aged, maybe middle-aged is 30 to 60. And then you have young, that's anybody under 30. Okay? Those are your blocks. That is done non-randomly. That is by how old you are. You can't prevent that. And then in each group, you run your own separate experiment. That way you can compare more and have less variation within your groups. Okay? So that's the idea of randomized block design. One block at a time. You can only do one variable at a time, and it helps reduce the variation within those blocks. Okay? So that's another way that you can design your experiment. The last way to design your experiment is what is called a matched pair design. Now there is one major limitation I circled in pink in the top right hand corner, and I'll even put a star, another 2 stars up here, is that you can only do a matched pair design if you have 2 treatments. So if you have 3 or 4 or 5 or anything more than 2 treatments, you cannot do a matched pair design. You're going to have to choose block or completely random. So what is a matched pair design? The idea is that there's 2 different ways you can do it, way A and way B. So way A is that you pair subjects up because they are very similar on many variables. Then one person gets treatment A and the other gets treatment B. Randomly, of course. So you create pairs of people that are very similar for many variables, not just one. And then randomly, one person in each pair gets treatment A, the other gets treatment B. Okay? So let me quickly talk about how I could do this with my example. Let's say I have my 100 subjects. Again, if you want to use more for replication, it's fine. I'm going to pair 2 people together here that are the same gender, same age, same knee severity, same diet, same exercise habits. Then I'm going to pair another group together. Maybe they're 2 girls that are both 25, that both have medium level of pain, and they both exercise a medium amount. Here's another pair. Maybe these are 2 older gentlemen, 2 guys over 60. They both have severe pain, and they both have really bad diets, but they do exercise a lot. Another pair here. These are 2 younger females, both under the age of 25. They both have very little knee pain. They both exercise once a week, and they both have average diets. Okay, the idea is you're going to make, obviously, 50 pairs. You're going to make as many pairs as you can, and these people are all going to be very similar within each pair. Then you're going to go to each pair and say, okay, who gets the placebo, who gets the new pill? That needs to be done randomly. So you can give them the number 1 and the number 2. Use a random number generator. First number that comes up gets the pill. Come down to here, same thing. 1, 2, randomly, somebody gets the new pill, somebody gets the placebo. You would do that for every single pill. Then what you could see is, if everybody that took the pill got better than their counterpart, then you really know that your pill worked because their counterpart was extremely, extremely similar to them, but it worked for the person with the pill, didn't work for the person who was on the placebo. So it's a way that you could get a lot of variables controlled at once and really have your experiment show that your new pill works. Okay? The other option for a matched pair design, the other way you could format a matched pair design is with where you pair subjects up with themselves. So let me explain this using a whole other scenario, and then I think you'll understand why my scenario was kind of bad for this. Let's say that you want to see if a new skin lotion will help get rid of mosquitoes or prevent mosquito bites. So, right, I have my arm here, and I have my left arm. That's a really bad left-looking arm. But anyway, I have my left arm, and I want to find another left arm that's very, very similar to this left arm. Well, the only arm that I could think of that is extremely similar on every level possible would be my right arm. So what happens is, one arm is going to get the mosquito repellent, one arm is going to get nothing, or maybe I put a fake, like a water-based lotion on if you need to use a placebo. And then randomly, who gets which is obviously going to be random. One arm could be the number one arm could be the number 2. Randomly, one of them gets picked to get the mosquito repellent. And then I can have both arms go into a bin of mosquitoes, and I can find out, does the arm with the mosquito repellent actually get less bites on it? So that's the idea of you pairing people up with themselves. You could also do a before and after. A before and after is a great way to pair people up with themselves, right? If I have a new pill that's going to help people lose weight, we'll have everybody weigh themselves before, have everybody take the pill, and then have an after result, right? So I can compare those results like that as well. That makes a lot of sense. It's hard to do it when you take a pill to pair somebody up with themselves. And I say this because go back to my pain relief, right? It's impossible for me to swallow a pill and say, okay, this pill, please go to my left knee, and then take another pill and say, this pill, go to my right knee. You're not capable of doing that, right? So you really can't do it. And then the other problem is some people say, well, how about you take the placebo for the first week and then stop and take the active pill the second week, or flip-flop. Take the active pill the first week, the placebo the second week. Well, the problem is that once you take a medication, it typically stays in your body for a certain amount of time, and what if it works and your knee pain then goes down, and then when you take the other pill the next week, your knee pain feels good, but it feels good because of what happened the first week, not what happened the second week. So you get the deal there. So a matched pair design where you pair people up with themselves is very tricky to do, but it does have a lot of value if you could do it the right way. Now, no matter what, both of these ideas of a matched pair design really help reduce variation, because when you pair people together that are very, very similar, it will really give you an idea of, did your pill work? And you can't say it was because of age, you can't say it was because of gender, you can't say it was because of the level of pain severity. It was held the same for every pair. The only difference was who was taking treatment A, who was taking treatment B. Okay, and obviously it's called matched pair, so you have to have pairs. That's why there can only be 2 treatments. If you have 3 treatments, there's no way to give out 3 treatments with pairs. Okay, so hopefully all that makes a lot of sense. Those are our 3 types of designs: completely randomized, block design, and our matched pair design. Last topic for this video is something that we call statistically significant. Let me explain, and then I'll give an example to end. If you end up an experiment and you say, my results were statistically significant, that phrase means a lot in our class. That phrase means that the differences we see in our treatment groups is too large to have occurred by chance. Okay? Meaning our explanatory variable did in fact do the causing. If the differences we see in our treatment groups is too large to have occurred by chance, that means you are statistically significant. Okay? Now, here's an example. Let's just say I have a new pill that's going to help people lose weight. And Group A takes the pill and they lose an average of 12 pounds. And Group B takes the placebo and they lose an average of 2 pounds. Our job as statisticians is to determine, are we seeing this difference? One group lost 12 pounds, one group lost 2 pounds. Are we seeing this 10-pound difference because of natural variation or sampling error. Hey, any two groups are going to be different. Anytime you have one group and you have another group, you're going to have different results. So is this 10-pound difference due to the fact that two groups are just naturally different, or is this 10 pounds such a large difference that it couldn't have occurred by chance, and bingo, my pill really does help you lose more weight? That's the idea of statistically significant. Now, to be honest, answering that question of, is 10 pounds a significant difference? That is something that's going to take us months and months to be able to learn how to determine. But right now, I just need you to understand the idea of what it means when we have statistically significant results. When we do have statistically significant results, it does tell us that the differences that we are seeing between our 2 or 3 or 4 treatment groups is because of our explanatory variable and not because of just chance. Okay? And I'm going to give you one more example, and really simple idea here. Let's say that we had, again, our losing weight pill, right? We had pill A and pill B. And we only had 10 people on pill A and 10 people on pill B, and we saw a 10-pound loss here and a 2-pound loss here. Okay? Well, that's only an 8-pound difference. Is 8 pounds meaningful? Well, we're going to answer that question someday, but let me give you this scenario. 1,000 people take pill A. 1,000 people take pill B, and on average, these 1,000 people lose 10 pounds. These 1,000 people lose 10 pounds. That's also an 8-pound difference. Which 8-pound difference do you think is more meaningful? This one right here. Absolutely. Hopefully you said that. Because if 1,000 people on average lose 10 pounds, that is significant. Whereas only 10 people losing 10 pounds, with 10 people you can have an outlier that really sways your data. With 1,000, that's harder. So that plays a part in it as well. So statistically significant is the idea that the differences we saw between our two treatment groups was so large that it could not have occurred by just chance. All right, hopefully this video helped to explain the different designs, and hopefully you guys can come to class ready to work on some problems.